All right, you know how every good story starts with that in the beginning bit? Well, today we're tackling the biggest beginning of all the Big Bang. We've got your notes here and this fascinating French text, lebigbang.txt. Looks pretty official.
Indeed. It seems to offer a comprehensive overview.
Hmm.
And, it's in French, always a reminder that scientific curiosity transcends borders.
Très bien. But before we get all existential, let's clear something up. This Big Bang, was there actually like a bang, an explosion?
That's the funny thing. The name is a bit misleading. It was coined rather sarcastically, actually, by Fred Hoyle, a physicist who favored a different theory altogether.
Oh, a little scientific rivalry to spice things up. Love it. So no sound effects then. What does the Big Bang theory actually describe?
It suggests the universe began from an extremely hot, dense state, roughly 13.8 billion years ago, and has been expanding ever since.
Expanding how? Like a balloon being inflated.
Precisely. Think of it like a rapidly inflating balloon, but instead of air, it's filled with, well, everything. Galaxies, stars, planets, the works.
Okay, so less of a kaboom, more of a cosmic whoosh. But how did scientists even begin to piece this whole thing together?
Well, they had to grapple with a pretty big idea. First, that the universe wasn't static. Edwin Hubble's observations in the 1920s showed that galaxies are moving away from us. And get this, the farther away they are, the faster they're moving.
So it's like a giant game of cosmic tag where everyone's it and they're all running outward.
Exactly, a very energetic game of tag, to say the least. This discovery was a game changer. It led scientists like Georges Lemaitre to develop those very early ideas about the Big Bang.
But from my notes here, it seems like it wasn't all smooth sailing for the Big Bang theory. There were other ideas floating around too, right?
Ah, yes, the steady-state theory. This model proposed a universe that was infinite and unchanging. To account for the observed expansion, they suggested that matter was continuously being created to keep the universe's density constant.
So as the universe expanded, new stuff just popped into existence to fill the gaps, like some kind of cosmic spackle.
In a way, yes. It was a clever idea, but ultimately didn't hold up against the mounting evidence for the Big Bang.
Evidence like?
Two crucial pieces, actually. The cosmic microwave background radiation and the abundance of light elements in the universe.
Okay, hold on. Unpacking time. Let's start with this cosmic microwave background radiation. That sounds a little ominous, don't you think? Like a cosmic microwave that's been left on for billions of years?
That's a pretty good analogy, actually. It's a faint afterglow, a whisper of energy left over from the Big Bang's intense heat.
So the universe had a really hot, fiery start, and this background radiation is like the residual heat.
Exactly. Think of the universe as a hot oven that's been slowly cooling for billions of years. The cosmic microwave background is that residual warmth.
And this radiation was something predicted by the Big Bang supporters.
Precisely. George Gamow and his colleagues, they calculated that this afterglow should exist if the Big Bang happened. They even predicted its temperature.
And they were right. Someone actually found it.
They did. In 1965, Arno Penzias and Robert Wilson were working on a new antenna when they stumbled upon this faint signal. Turned out, they'd accidentally discovered the cosmic microwave background. A serendipitous finding that earned them a Nobel Prize, I might add.
Wow, talk about being in the right place at the right time. Okay, so we've got this leftover heat from the Big Bang. What about that second piece of evidence, the abundance of light elements?
Right. So the Big Bang model predicts that certain elements, hydrogen, helium, lithium, were forged in the intense heat and density of the early universe, a process called Big Bang nucleosynthesis.
The universe started with a bang and a whole lot of cooking.
You could say that. And the amount of these elements we observe in the universe today, it matches the Big Bang's predictions incredibly well. Another point for Team Big Bang.
Okay, you've convinced me. The Big Bang definitely happened. But our notes here also mention some problems with the theory. What's the deal with that? It wasn't all smooth sailing from there.
Not quite. The evidence was mounting, but some cosmic puzzles needed solving. Puzzles that, oddly enough, pointed toward an even more mind-blowing chapter of the Big Bang. So you remember those cosmic puzzles I mentioned?
Oh, absolutely. Those really stuck with me. It's like, if the Big Bang started everything off in one tiny, chaotic space, how do we end up with a universe that seems, well, oddly organized?
Precisely. The universe is remarkably uniform on a large scale, almost like a perfectly stirred cosmic soup. This is what we call the horizon problem.
So no cosmic lumps or swirls or anything. Everything's a bit too blended for something born from, a bang.
Exactly. And it gets even weirder. Einstein's theories tell us the universe could have any curvature. Like, it could be shaped like a saddle, a sphere, you name it.
Right, right. I remember that from physics class.
But observations show it's incredibly flat. This is the flatness problem. Imagine flipping a coin 1,000,000,000,000 times and getting heads every single time. The odds are astronomically against it.
Yeah, I wouldn't take that bet. But we've got one more problem on the list here. Something about monopoles. Okay, now you're just messing with me, right?
Not at all. This one is a real head-scratcher. Some physics theories predicted that the early universe should have been teeming with these things called magnetic monopoles.
Hold it, back up a second. Regular magnets, I get North Pole, South Pole, opposites attract. But a monopole, that's just a North Pole or a South Pole, all by itself.
Precisely. And according to some theories, these monopoles should be everywhere. But we haven't observed a single one, ever.
Okay, that officially goes in the weird even for the universe category. So what do we do with these problems? Just kind of ignore them.
Not so fast. These problems were huge clues. They told us there was something big missing in our picture of the Big Bang. And that something is a mind-blowing concept called inflation.
Inflation. Now that sounds oddly familiar. Isn't that something I should be worried about at the grocery store?
Not this time. Cosmic inflation is actually a good thing, trust me. Picture this. In the first fraction of a second after the Big Bang, we're talking a TINY fraction, like a billionth of a billionth of a billionth of a second, the universe went absolutely bonkers and expanded at a truly unimaginable rate.
Okay, we're talking faster than light.
Well, not quite faster than light itself, but faster than the expansion we see today. And it's allowed by Einstein's theory of relativity.
Okay, so how does this inflation thing explain all this cosmic puzzles we talked about?
It all goes back to that tiny uniform speck we talked about, the one that was smaller than an atom. Well, imagine that speck suddenly ballooning to become unimaginably vast. During inflation, any initial lumps or bumps in that tiny region would have been smoothed out, like stretching out a wrinkled piece of fabric.
So inflation solves the horizon problem. That initial uniformity wasn't some big mystery. It was just a really, really blown up version of a tiny starting point.
Exactly. And remember, those unlikely conditions needed for a flat universe. Inflation takes care of that too. It stretches out any initial curvature. Think about blowing up a balloon. The surface seems flatter the bigger it gets.
Right, right. Okay, that makes sense. But what about those missing monopolists? Did inflation just blast them away to another dimension?
In a way, yes. Inflation diluted their density so much that they would be incredibly rare in the vastness of the inflated universe. It'd be like trying to find a single grain of sand after it was scattered across a whole beach.
Okay, so inflation smooths things out, stretches things flat, and makes things incredibly hard to find. Kind of like my teenage years, now that I think about it. But seriously, this is amazing. It seems like inflation explains all those problems. But how did it happen? Where did all that energy come from to power this cosmic growth spurt?
That is the million-dollar question, and one that physicists are still working on. The leading theory involves a hypothetical field called the inflaton field, a hidden energy field permeating the early universe.
The inflaton field. You know, it's funny you should say that because it reminds me of something. At the very beginning, are we talking about what might have come before the Big Bang? Now? Okay, so we're going way back. Even before the inflaton field kicked in, things got really crazy. What's back there? What are we talking about here?
We're venturing into the realm where our understanding of physics starts to get a little fuzzy. We're talking about the Planck epoch.
Planck epoch. That sounds intense. Like a workout routine for my brain? What even is it?
Think of it this way. The Planck epoch is named after the Planck scale, which is the smallest possible unit of measurement, for anything.
Yeah.
We're talking smaller than small. The absolute limit of what physics can describe.
So smaller than that box you're not supposed to open in case you unleash some cosmic horror. We're really pushing the boundaries here.
We are. The universe during the Planck epoch was so incredibly hot, so dense, that it's thought all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak forces they were, all combined into one single superforce.
A cosmic force to rule them all? So what happened? This superforce got lonely and decided to break up into a bunch of smaller forces.
Something like that. As the universe expanded and cooled, this single unified force separated into the distinct forces that we observe today. A cosmic breakup, if you will.
Man, that's gotta be rough on the old universal fabric. But if everything we know about physics kind of breaks down during the Planck epoch, how do we even begin to study it? That's like trying to study a black hole with a flashlight.
It's a challenge, that's for sure. Our current theories, things like Einstein's general relativity and quantum mechanics, they just don't quite work at those energy levels. To crack the code of the Planck epoch, we'd need a new physics, a theory of quantum gravity.
A theory of everything. Now we're talking. That's got to be the holy grail of physics, right? Finding that theory.
It is, and it's one of the biggest unsolved mysteries in physics. But even though we don't have all the answers, thinking about the Planck epoch, it leads to some pretty mind-blowing questions. Like, what, if anything, came before the Big Bang? Was there a singularity? Or something else entirely? Another universe, maybe?
Okay, whoa, another universe. Now you're just messing with me.
It might sound crazy, but it's a possibility that some physicists are exploring. The truth is, we just don't know. But hey, isn't that part of what makes studying the universe so exciting?
It definitely keeps things interesting. This whole deep dive has been incredible. We've gone from a tiny point expanding faster than you can imagine to a universe full of stars, galaxies, planets, even life. It's mind-boggling. And to think we're just starting to scratch the surface.
Exactly. Every new observation, every new theory, it brings us one step closer to understanding our place in this grand cosmic scheme. And who knows what incredible discoveries await us just beyond the cosmic horizon.
That's right. And for our listeners, if there's one thing you take away from this deep dive into the Big Bang, it's that the universe is a much stranger, more wondrous place than we could ever imagine. So keep looking up, keep asking those big questions, because it's that curiosity, that drive to explore the unknown, that makes this journey of discovery so awe-inspiring.